So empirical formulas. The empirical formula that derived from some chemical analysis is an expression of the mole ratio, i.e. the smallest whole number ratio of the different atoms in the compound. So why do we talk about an empirical formula versus a molecular formula? The actual molecular formula may be an integer multiple of the empirical formula because it has to do with the actual number of different atoms in a discrete molecule of that compound. So for example, C2H4O is the empirical formula of C2H4O, but it's also the empirical formula of C4H8O2, C6H12O3. And the way to think about why it is important is, let's say you're measuring some sample and you do some sort of elemental analysis and you know, okay, this sample is this percent carbon, this percent oxygen. Can you tell the difference by mass between two molecules of C2H4O and one molecule C4H8O2? No, because they have the exact same mass. They'll have different properties, and we'll get into that, at various places in the semester. But just by mass, you cannot tell the difference of the two. So by mass, if you have the percent composition of a compound by element, you know how much element is in it. You even know the ratios of elements in it. All you really know is the empirical formula, not the molecular formula. So just a quick quiz to make sure you're following. Which of the following is the empirical formula for C2H6O2? I'll pause. It's ethylene glycol, antifreeze, so useful, important chemical. Which of the following is the empirical formula? Okay, so the answer is C. Because if we look at C2H6O2, CH3O is just, all the numbers are exactly half of that. So if we have two molecules of CH3O and one molecule of C2H6O2, we can't tell the difference. So the empirical formula is the lowest common denominator there. If you look at C4H12O4, that would be another multiple. There'd be a different molecule there. Actually, there's a bunch of molecules with that formula. But that would be the empirical formula is the lowest common multiple of that. So that's the empirical formula. So let's say ribose, sugar present in the cells of all living organisms, has an empirical formula of CH2O and a molecular mass. How do we get it? We won't get into that now, but it has a molecular mass of 150 atomic mass units. What is the molecular formula rather than the empirical formula? Well, what's the mass of a single unit? A mass of a single unit of CH2O. We know the mass of ribose is going to be some. If the molecular formula of CH2O is a multiple of the empirical formula, then the mass must be a multiple of the mass of that empirical unit. So the mass of the mass of the unit CH20 is going to be 12.01 grams plus 2 times 1.008 grams plus 16.00 grams. That equals 30.03 grams for a CH2O per mole of CH2O. So if we have a 150 grams per mole is the molar mass of our entire molecule, and then we have 30.03 grams of 1 unit of this per mole of a unit of this, then we can rewrite that as that's the number of grams per unit per mole of the unit. Then when we cancel this out, we're going to get, this per gram, 30.03 grams per mole of a unit. We cancel out the grams, cancel out the grams and the moles, and we get 4.995 units. Now we know that we can't have, it's very unlikely that, we can't, sorry, say it again. We can't have a fractional number of units of this. You can't have fractional number of molecules. So the conclusion would be, there's some experimental error in the determination, right? We said it's 150 AMU. That could either be 2 or 3 significant digits. So our answer is either 2 or 3 significant digits. And to 2 or 3 significant digits, it's 5. So there's 5 copies of CH2O in ribose, which means the molecular formula would be C5H10, multiplying that by 10, O5. So that would be the molecular formula given the empirical formula and the molecular mass.